All right, so I am now recording. So today we're looking at chapter 8. So last class we talked about discrete systems or discrete probabilities. And now we're going to look at continuous probability distributions, which is the one that you're going to see a lot more often than the discrete ones. All right. So we're going to look at two different types of distributions. We're going to look at a uniform distribution and then a normal distribution. So the uniform distribution we're going to look at first is actually really quite quick and easy. It's basically a rectangle. The normal distribution is what's pretty much everything after this point is going to be based on. So that's going to be the big thing that we're going to spend a lot of time looking at. All right, this is a continuous uniform distribution. A little bigger for you. So a uniform or continuous uniform distribution is where every possible option has the exact same probability. The probability is always going to be 1 over b minus a, whatever the two endpoints are. Your mean in your standard deviation, your mean is always a plus b divided by 2. So it would be right, whatever is right in the middle of those two. And the standard deviation is b minus a divided by the square root of 12, always. So those are the three formulas you would need for a continuous uniform distribution. All right. So let's look at a problem. So the first thing we want to look at is let's figure out what the actual distribution looks like. So in this case, we're looking at frozen French fries. The final package weight is thought to be uniformly distributed as a random variable, has a uniform distribution between 57 ounces and 63 ounces. So the bag probably says 60 ounces on it, but it's somewhere between 57 and 63. So we look at our little distribution. So 57 would be there, and 63 would be there. The height is 1 over b minus a, and that's going to basically be what your probability is. So it's 63 minus 57. So the height of the rectangle is 1/6. For it to be a probability, what does the sum of the whole thing have to be? 1. What's the width of the rectangle?
1.
No. What's 63 minus 57? So my width is 6, and my height is 1/6, right? How would I find the area of a rectangle?
Sorry.
You're making your life way too hard. Huh? Yep. No, that's perimeter. Areas is multiplied. Length times width. What's 6 times 1/6? 1. So the area is right. Okay. We were looking for to make sure that the probability has to be 1, correct? So we said that the height is 1/6 and the width is 6. From 57 to 63 is 6 spaces. So that means my area is 1. So whatever the space is inside that box, this all is 1. That's my probability that this would occur. So therefore my probability is 1. So therefore it's a distribution. Okay, remember we have to ask everything, the probability has to be between 0 and 1, and the total has to add up to 1. If everything my probability is 1/6 and my total is 1, we're good. Okay. All right, so we've got that. Yeah.
Where did you get the 6 from? Is that the 6 that you got from back?
Yep, 53 or 63 minus 57. All right, so the next question says, what is the mean weight for the package? So what was the formula for mean?
57 plus 63.
Yeah, 63 plus 57 divided by 2, which should be 60. So 60, and that's my mean. And that should make sense. It should be right in the middle, right? If everything is equal, it should be in the middle.
The median.
And most of your normal type distributions, median and mean will be the same. The only time it's not is when it's skewed left or skewed right. We talked about that. All right, next question. What is the standard deviation for the weight of the package? So standard deviation was B minus A divided by the square root of 12. So $63 minus 57 divided by the square root of 12. That I can now. Oh, it's going to be a decimal. So I got 1.73. So that's my standard deviation. Okay. Get it? Okay. Because as with any kind of distribution or any kind of data, you're always going to have to be able to find your mean and your standard deviation. Those two are the most important pieces of information that you're going to need. And we're going to use them a lot tonight. All right. Next question. What is the probability that a store will receive a package weighing less than 59 ounces? So 59 is over here, right? So we want that space right there, correct? So what's the area of that rectangle?
Just a fraction of 1.
So what's the width? We went from 57 to 59, which is 2, correct? So 2, and what's the height? 1/6. So 2 times 1/6 is 2/6 or 1/3. Or 0.33333333. Yeah. Yeah. Okay. Next question says, what's the probability the package will contain between 60 and 63 ounces?
I mean, 3 times 1.
So we're looking at this spot right here, right?
Yeah.
So it'd be 3 times 1/6.
Okay.
Now, that's 1/2, right? You should have been able to figure that out without actually doing any math. What was the 60?
What was it, half of the square?
60 is the median, right? Or the mean. So it's literally that splits it in half. So we're looking at the upper half, that has to be 50%. All right, what's the probability the package will contain more than 62 ounces? Which is 1, right?
Yeah.
Times 1/6. So that's going to be 1/6. What's the probability to contain exactly 60 ounces? Zero.
Exactly what?
60 ounces.
How did we get the 1/6 on the last one?
62 to 63 is 1, right? Times 1/6. So the problem when if you notice when we're doing this problem, we're looking for area, right? In essence, to find it. If we're just at one number, the width is 0.
So none of them are like exactly.
Right. You're never going to get exactly that. You can get there's always going to be slight variation. So what you end up doing later on, when we're looking at for exact values, you will go a little below it and a little above. You typically go a half below and half above. So if we're going to look at exactly 60, in this case, I would look from 59.5 to 60.5 to get that range. This question didn't ask that. This question was literally trying to get you to realize that you can't find the area of a straight line. So, okay. All right. That is uniform distribution. It's literally just a rectangle because all the probabilities are going to be the same. Remember this? I think we talked about it in chapter 4. Yeah. This is your bell curve. This is typically known as a normal distribution. You can have normal distributions that are not bell curves. However, once you get past a certain number of values, they typically fall into a bell curve shape. Okay. Rules are still the same. All probabilities have to be between 0 and 1. The total still has to equal 1. However, unlike the uniform distribution that we had, your normal distribution will go on forever in both directions. So therefore, you never actually end up reaching 1. Okay. When we're looking for the probability, we're going to be looking at areas under the curve. You are not going to have to do the actual area under the curve. That my calculus class does. You guys are going to, I'm going to show you a table that you guys, and I totally forgot to print it out today. But you guys will be able to find it. And it's also in the book too. So if you have the book, you'll be able to pull it up. We're going to use what's known as a probability table or a Z table that's going to have all the numbers in it for us. And we're going to be able to do the calculations based on that, which makes my life a lot easier. Yeah, my calculus class actually has to do the area under the curve for their Calc 2 class. So, because that's the only way to find a true area under the curve. All right, what was the information that we talked about when we originally did this problem? There was a rule we did. Huh? We did talk about the left skew and the right skew, but there was a rule to tell me percentages under the curve. The empirical rule. What was the empirical rule? So 68, 95, and 99.7. That was 1 standard deviation. That was 2 standard deviations. I always get those mixed up. Correction. Hold on. That way. Okay. And that was 3 standard deviations. Other way. Okay, so that was 1 standard deviation, 2 standard deviations, and 3 standard deviations. That rule works really well if they are 1 standard deviation, 2 or 3 standard deviations. But what if we wanted to find 1.2 standard deviations away? It's not going to help me as much. Okay, and that's what we're going to be looking at tonight. But that is a good rule to generally understand, so you can get some good information from it and quickly understand what's going on. Okay. So I'll show you this. So this is where we had the 1 standard deviation. You can see that that's 68. Approximately 68, not exact, or it's a little higher. And then we have 2 standard deviations. And 3 standard deviations. So you've got the 6.6826, 0.9544, and 0.9975 or 4. So when we're looking at these, all the percentages that you're going to get will be done out to 4 decimal places.
So what, how many would 4, what many percentage was 4?
99.99, something like that. The tables only go up to 3.9 or 3.99. So 3.99 gives you 0.99997. That's why when we were looking at it originally, we said basically anything over 3 standard deviations, you're golden. You're going to get pretty much everybody. So pretty much everything is between -3 standard deviations and +3 standard deviations away from the mean. After that, you're in the very, very rare or outlier situations. So I'm just going to share this screen because I don't feel like actually copying them all over. So if you look at it, this is a very small sample. There's only 25 people they sampled at it, and you can get it jagged. You kind of have a little bit of a curve here, but it really is flat out. You go down a little bit more. This is another one, a very small sample, only 25 people. This one does have a little bit more of a bell shape to it, where you have that middle spike. When you get into some more of the larger samples, now this one has over 200 samples, you have a little bit better bell curve. It's not very symmetrical, so this one would be skewed to the right because there's that tail that's out to the right in here. But you do have a little bit more of a bell curve shape with that. So the curves that we were looking at, really annoying me. Okay. Logging into all these different things now. This. All right. So here's my normal bell curve. If I want to find the area or the probability all the way up to 2. So this whole so we could use the empirical rule because I'm going up to 2 in this case. But let's look at a few little things first. What is it going to be from that spot to there? What percentage? Right. Why? That's half of it, right? So whatever we're getting, you can always look at it individually on both of the sides. That's 50, and if we figured out from 0 to 2, I would get that piece there. The table that we're getting that you're going to use is known as a Z table. You can look this up if you do a quick Google search. If you have your book, it's literally in the back of your book. So if you have the book, just go right to the back of the book. It should be, yeah, it's the Z table. If you don't have your book, you have a computer, just go to Google and type in Z tables. It should be actually z-table.com will be the one that I'm actually going to use. That's this one. So what the Z table has is it has columns and rows. The first column is your first digits. So it's always going to be, so the Z of 0 is right in the middle, 0.0, 0.1, 1.0. That's going to be the first pieces of information. The top row gives you your second decimal place. Okay? So we were looking for 2, exactly 2. So we were looking at 2.00, which is right there. So whichever table you're looking at, if you don't have a table, tell me and I can come help you find one. Because everybody needs to be able to look at one. And make sure you can find that number on your table. You got something? Yeah, that's right. So 2.0.
Oh, okay.
So you got it. I just have one that I can actually highlight it so you can see it on my screen.
Yeah.
I love that. There you go. Go ahead. Because then you can actually, so you're doing a 2.0. You're going to spread out a 2.0. Yeah, so you're looking at 2.0. Yep. Got something? It should be. I actually should have looked at it before I came down there. Oh, look, it's not. Right there. It's the -1, and then the other page is the +1. You got one?
I'm not sure if I'm on the right table.
Yep, that'll work fine. So this is the -1. And that's. Oh, actually, you're not on it. Oh, you know how to do it. Oh, no, it's fine. Close. They don't want more ads. Negative. Positive. 2.7.
Yeah, thank you.
If you go to appendix A, it's the first one. Positive or negative positive. You got one, you got one. You got one? Because we're gonna use these a lot, so. I totally pressed. Good, 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 good. Okay, everybody's got one.
Yeah, okay.
All right. So this table, if you notice where it says 2.0 is 0.97725. Okay. So that is the area under the curve from the left all the way to that number. Okay. So it's not counting from the middle, it's counting from the left over to that number. All right. Does that make sense or no?
Wait, but what are the probability levels in the table? So
Where?
like 0.1, 4.0, 1.
That's the second decimal point. We're going to do those in a second. We just did exactly 2.000 basically. So we did the exact number. We're going to come up with ones where we're going to have to move over and I'll use those other ones. Okay. So the number is, it's all the way over from the left. That's important to understand. So if we looked at, let's say, let's do negative 1.52. Okay. So now you're going to look at the negative Z table. And we're going to look for negative 1.52. No,
It's like, yeah.
because you'll see in 1 second. So negative 1.5, and then you're going to go over to the 2 column. So negative 1.52, you're going over to that third column because it's 0, 1, 2 for the last digit. And you should get 0.06426.
The 0.02.
Yes.
So like if it was, 1.54, you go 0.4,
Right. Yep. So that right there is the negative 1.52. So if I went negative 1.53, that's there, 1.54. That's what that second, that's what the column or the row at the top tells you, those decimal points over. Okay. Huh?
This one goes backwards. The zero is over on this side.
Oh, okay. All right. So that number is again from the left to that point. So that's telling me the area, all of that is that probability. Okay. So it's always from the left to that number. Correct. So basically what that tells me is that anything that is less than negative 1.52 standard deviations away is going to give me that probability. Okay.
that's 6.4%.
Correct. Yep. I forgot to. .06426. I forgot to copy it before I used it. What if I just want that area? From 0 to 1.27.
Would you just calculate, subtract what you get for the one? At the 127, subtract it.
Subtract from what? Not from 0,
Then
50%. Because the 50% is that other half that I don't want. Okay? So I don't want this section over here, which is 50 or 0.5. I don't want that. So whatever number I get, I'm going to subtract the 0.5 from because it goes all the way over. Okay? So was it 1.27? You should get 0.89796. And then we would subtract the 0.5 from that. So that area right there is going to be 0.39796. The Z table. So we went from 1.27. What what does it say?
The numbers are- We have,
yeah.
Or is it? I think you guys have what, 4 decimal places? So you got 0.9 or 8980. Yeah, that's fine. It's just a rounding. The table I'm using goes to 5 decimal places. Most times 4 is fine. So
Can you go back to that? 1.27?
because my Z that I was using is 1.27.
Oh, okay. So it goes by the number.
Yes. Not the decimal. It's the that top row is your second decimal point. So since I'm looking at the 7, 1.2 is the row that I'm looking at, and then 7 is the column. All right. What if I wanted this section? What would I do to find that section?
We have to find 0.56.
Add it.
1.56 and subtract that. I mean, go to like positive table.
All right. So step 1, very good. Let's find what 0.56 is on my table, right? No matter what, we still need to find that piece. So let's go to the table and find that. All right. So 0.56, let's look for that one. So, yeah, so 7122, and your guys 71223 or 7123, right? All right. So 0.7123. I'll round to four decimal places so everybody's in the same spot. All right. So does that look like it's going to be 0.7123? Why?
That's the outside.
So so the piece here has to be less than 50, right? Because if it's not less than 50, it's not working.
Just one.
Right. So since I want the opposite or the converse of it, I do one minus it. So remember the complementary? So I would do 1 minus that. So 1 minus that would give me this area here. So 0.2877. Yeah. So that'll give me the 0.2877. So that's the probability in that piece there. Okay.
So when it's that, you're doing that side, you do the 1 minus.
When you want the opposite direction, remember the number you're going to get in that table is always going to go from the left to wherever you are. If I want the opposite side of that, I would do 1 minus that. All right. Find me this one. That sounds about right. I didn't do the actual calculation, but that sounds close. How'd we do it? Right. So when you're looking for between two, find 2, which is 0.9773, according to your tip. 9772. Okay. And then 1 is 8413. Yeah. And then we subtract those. Because remember, it's going all the way over. So this is going to give me this all the way over to 2, right? and the 1 is going to get me all the way over to there. I want the difference of those two. So find them both, subtract. So I haven't done it yet. That's right. So that's the answer between the two. Good. All right, let's use the table a little differently now. What's Z?
One item, a window, one.
No. We're so all the way up to this point, I've given you the Z, and you've looked and find me the probability, right? And this one, they gave me the probability. We have to find the Z. So you're just going to use the table the opposite direction. So we're looking for 0.9147. So we look at the table. 0.9147 is right there. So it's 1.37. Okay? It's just the opposite direction. All right? So the Z-score is telling you how far away, basically whatever your standard deviation is. Okay, it's how far away from the mean, or 0 in this case, you are. Positives to the right, negatives to the left. We can do it where if you have the Z, we can find the probability. Or in this case, we can do the other direction. Do one more of these before I go on to the next one.
Theoretically, we have to speak one, right?
What do you mean?
Well, actually, I don't.
So Z is not a probability.
Okay.
So you can't add the Z to the probability and get anything. It's a number of standard deviations from the mean. So when we first started looking at it, we just had 1, 2, 3. It was the simple ones. But not everything that falls in life is simple. So we have to have that variety. And instead of having you do out the calculations and try to figure out the exact value of it using the formulas, we've got a table that can give me the answers for it a lot easier. Because the formula is not that easy to use. All right, find me my Z.
Correct. Correct. You have to add that to 0.5 and 5 that. So we're going for 0.665.
Why?
Because you have to add that to the other half.
Right. Remember, the number you're looking at the table is going all the way from the left. You're not going to find well, you might find 0.3665 in there, but it's not necessarily going to be it's not going to be the right answer. So yes, so you have to add the 0.5 to it to find that percent in the table. Because remember, the actual number that you're looking at in the table is all of this. But I didn't have that there. So when we're looking in the table, I'm not going to find that number. I'm missing the other half. So I'm going to add the 0.5 to it to find that number in the table. So it's 1.11. Yes. Yep.
But why would you only have dividends?
Because the same problem that we did back when we did this one. You can have, when you're looking at just an area, if you think back to the uniform distribution that we did at the very beginning, we were looking at between 59 and 62, 63. We were looking at specific sections of them. So it's not necessarily always going to be the whole thing you want. So this more is just making sure you understand how the actual like picture the graph works before we start moving into the application style problems that are going to have us do a bunch of different numbers to figure out actual calculations from them. All the ones that I showed you here were on the table, but you can see this a few different ways. How it's written, I should say. So we're going to use that. So this one, you could see it as 1.27. You can see it written like that. If I wanted less than that, I could say Z is or less than or equal to 1.27. That would be the other direction. You also can see it written as P of 1.27 is less than or equal to Z is less than or equal to 3. You can see it written like that. They all mean the exact same thing. Okay. Well, that one doesn't. That one's different. But those two mean the exact same thing. So depending on how they write it and depending on how they show it, they might not show you the graph and say, find me this area. They might show it to you and say, find me the probability of between those two Z's. It means the exact same concept, exact same thing we were doing. Yeah, let's do this section first. All right. So far, all the ones we've looked at started at 0. Not all tables are going to start at 0. So to use our information that we have and to have the table work, we need to have a formula that's going to help me find that Z. This is the Z formula. This will allow us to take any problem that we're working with, any application, and turn it into a Z-score that I can use to find in the table. Even if the mean is not 0 and the standard deviation is not 1, which is what we were just looking at. So the formula is whatever value you're looking for, so that's the X, minus your mean, divided by your standard deviation. So the 3 pieces of information you're going to need to know to do these is what are you looking for, what's the mean of your data, and what's the standard deviation of your data. Okay. Because remember, the bigger the standard deviation, the more wide, the wider that thing is going to be spread. So that changes things. Whatever your mean is, that's going to change where your peak is. All right, everybody got that formula down? All right, let's use it. So find the probability that a normal random variable with a mean of 10 and a standard deviation of 20 will lie between 10 and 40. So right now, you can't go to your table and look up 10 and 40. We don't have those. Okay. We need to standardize that information, and that's where we use the z-score. Okay. So I need to find the z-score for 10 and 40.
I need to not have those.
I know. Don't pay attention to the way the numbers are. Actually, 20 shouldn't be halfway between the 25 should be. Because there's 10 numbers between 10 and 20. There's 20 numbers between 20 and 40. So.
Actually, that makes sense. Yeah.
Yeah, it's every other one. So these three right here are 10 apart, and everything else is 20 apart. Yeah, it wasn't a very nicely made up graph, but they did it because 10 was the mean. So let's find if my x is 10. So I know two pieces of information they gave me. My mean is 10, and my standard deviation is 20. So if my x is 10, I need to find my z-score. So I have 10 minus 10 divided by 20, which in this case is 0. Okay? So my first z-score is 0. Now when x is 40, I do the same thing again. I do 40 minus 10 over 20, which is 1.5. When you do the calculation for z, you're always going to round to 2 decimal places because that's all your table has. All right. So now we can go to our table and we're going to find when z is less than or 0, less than or equal to 0, and when z is less than or equal to 1.5.
How did we know it was less than or equal? Was it a minus?
Mm-mm. Because these always, when you're looking at that table, if you're looking at for a single variable, you're always looking for, it's always going to be less than. Because it's always going from the left over to it. What we want the 0 is less than or equal to z is less than or equal to 1.5. That's the final answer I want. But since I have 2, we have to take both of those and do what to them? We have to take the 2 pieces and subtract them because I have the beginning point and ending point. So we're looking for the 0, we're looking for the 1.5, and now I'm going to subtract those 2. So my final answer is 4332. So 43.32% of all the values will fall between 10 and 40.
Doesn't that same percentage will fall between -10 and
Yes. No, not -10 and -40.
no.
It would be between 0 and -30.
Yeah.
It's got to be the equal away from it.
I mean.
Or actually 10
it's like
to-
easier with the.
Yes. Well, and that's the point of taking it with the Z's. When we get the Z-score, that brings my mean back to 0. So that's normalizing it so that I can look at it in terms of my tables and everything else that I have. Okay. And that works as long as I know that it's a normally randomized variable.
So did you like put that in the calculator or?
No, I use the table.
Oh,
You have to use the table to find those two, and then I just subtracted them. I subtracted them. Well, I did that subtraction in my head. But
What did you take away from 1.5 to get 4.332?
I didn't take anything away from 1.5. I subtracted the 0.9332 from the 0.5000.
Oh. So you subtract the 0.5 from the 0.9.
Well, yeah,
Yeah.
9.332 minus point. Yeah. So, because I'm taking the two endpoints and I'm going to, because remember, those always go all the way back down to the left. All right, one more, and then I'll give you guys a chance to do one. All right, so suppose the National Testing Service gives a test in which the results are normally distributed with a mean of 400 and a standard deviation of 100. If you score a 644 in the test, what fraction of the students taking the test exceeded your score? And yes, this is based on the SATs. They just couldn't say that. So this is where, remember I said, if you want to go grab those little sticky notes or be able to draw a bell curve, this is where drawing bell curves really help you. Okay? Because, huh?
I think
They haven't come in yet. Hold on. Really? All I'm getting is books. I don't want books. There we go. Hold on. I'm buying things. Give me a second. All right. I'm free Wednesday. They should be here tomorrow. Because if you get the little sticky note, you can make a nice little bell curve that looks like this. And it really does help you to shade in those sections to see where you're looking. Okay. Because if you're just trying to do it visually in your head and trying to which direction you're going and stuff, you're going to screw things up. Being able to draw it out and not have to get your perfect bell curve every time, because those are annoying, makes your life a lot easier. So The SATs actually is standardized. It is standardized for that you would get a 400 on the math and 400 on the English. And the standard deviation is set to be 100. Every single time that they start to notice that is skewing, where the number is getting higher, they adjust the test to keep that right around there. So the funny part about it is it's getting easier and not harder. So they've changed the actual numbers. So like you really can't compare your score to somebody who took the SATs 3 or 4 years ago, because the scores would not be equal because it's based on your test. So mean of 400, standard deviation 100, you scored 644. Yeah. So step 1 is to what? I need to find what? I need my Z. I need my Z score.
I mean, your score is 2.44 and then deviation. Oh, wait.
Right. So 644 minus 400 divided by 100 is 2.44. So that's my Z score. Step 2, go to the table and find 2.44. Yep. 0.9925, right? 0.9927 you have?
Yeah.
Oh, you're right. I'm off by 1. Okay, 9927. You're right. I was. So the probability that Z, actually, what we got was 0.9927. Okay. But that's the other direction, right? So I'm going to do 1 minus that. So the probability that Z is greater than or equal to 2.44 is 0.0073. So 0.73%. If you got a 644 on your SATs in either section, only 0.73% of all people who took the test scored higher than you. Remember what you were asking me earlier? What's it for? If you got an 800 on the SATs, what's your standard deviation? What's your Z?
Like, it's the-
No, what's 800 minus 400? 400 divided by 100 is 4. Look at the very last number on your Z table. Because your Z table only goes up to 3.999 or 3.99.
I don't.
So it's like 0.99999 just keeps going. Does yours go to the book one go to 3.99? 3.4? So even if you look at 3.4, you're still at like 1 out of every or 3 out of every 1,000 people. When you get up to the 0.99, you're looking at 3 out of every 10,000 people. Okay, so that's why you don't see very many perfect SAT scores. All right, let's have you guys do one, and then we will take a quick little break. Yeah, sure. Go ahead, ask a question. Oh, take a picture of that. You can more than welcome to take a picture. All right, your turn. So step one,
Good idea.
find your z-score. So you're,
It's just the, like the area that you're, the range,
yeah, so we're looking at between 100 and 150.
so X is gonna be.
No, X will be 100 and X will be 150. You have to do two.
Oh, yeah, yeah, you did,
Like the first one we did when we did between 10 and 40. So you have 100 minus 234 divided by 94, and 150 minus 234 divided by 94, and you get negative 1.43 and negative 0.89.
kind of different for you.
So that's what we're looking for. So we're not subtracting those two numbers. What do we have to do next?
And you just put the,
Right, you have to find the actual probability from the table. And remember, probability is always going to be positive, right? So if you type the numbers in backwards on your calculator, you just get the negative of that. You get negative 11.1103. Just for reasons you can't have a negative, so just get rid of the negative sign. It's going to come out to be the same. So the probability when you plugged it in for negative 0.89 should have been 0.1867. And the negative 1.43 is 0.0764. Subtract those two. So the probability that your next purchase will total between $100 and $150 is 0.1103 or 11.03%. And while the grunt worker working at the cash register doesn't do this, there's people in the offices that actually do these calculations to determine how many people they need to have on and how much merchandise they need to have and how much money they need to have in the store and all this other stuff to figure these things out. Okay. All right. Go take like a 10-minute break. Be back at 7 o'clock. We're probably going to be out of here just after 8. It's not going to be that late. I don't have a ton more to go. It helps that I'm only doing one chapter a night now. Just take a picture of it, of the question, and text me it, and because most of them actually were pretty straightforward. But if you take a picture, I can tell you exactly how to do the one you're looking at. Yeah. Oh yeah, I can store the proof slide. Sure. That one. Yeah. So
I'm not understanding the correlation between the 5, 6, 5, 4, 3, 2, 1 and the.
okay. So when you're rolling a sum greater than 5,
Mhm.
if you're looking at the actually let's pull it up. So here's a little chart. So it what was it? No, that was
Oh,
the
no.
scores.
Mhm.
That's okay. That one. So 6.
Mhm.
There's 1, 2, 3, 4, 5 sixes out of the 36.
Okay,
Yes.
thank you.
You're welcome. All right. Did I copy that one? I did not. All right. Body temperature of adults are normally distributed with a mean of 98.6 and a standard deviation of 0.73 degrees Fahrenheit. Which temperature represents the 90th percentile? So how would we go about doing this? What do we know? Huh? What's the mean? All right. So we know the mean is 98.6. Okay. And we know the standard deviation, right? Okay. So let's make a nice little bell chart. Oh, I need a blank bell chart. I lost my copy of my blank one. There we go.
the word. The 90 percentile is like 90% of the area.
Yes. So we know 98.6 is here, right? And we're going to go up by 0.73, so we can go up those. That's fine. But we want to know, so this is 50%, correct? So I know it's going to be somewhere over here. Not quite sure where, so we'll just put a line there. So I want to know, with that being 0.9, that. So I need to know that number right there. And when we look it up, that's going to be my Z, correct? Okay. So find me my Z, that's going to give me 9.9000.
That
So you get the closest one to it.
90147.
I think 0.8997 is probably closer. So what are we at? 1.28? All right, so 1.2. So we've now taken the 90%, we changed it into a Z-score. And I know that equals X minus the 98.6 over the 0.73, correct? Sorry, we have to do a little algebra. Because I need to find X. So how do I solve for X? Yep, multiply by the 0.73. No, the 1.28. We want to move that out of the bottom. So I get 0.9344 equals X minus 98.6. And now we add the 98.6. So 99.53.
Is it 1.28 times 0.73?
Yes. So you multiply this whole thing by 0.73. And then we added the 98.6. So 99.53 would be in the 90th percentile.
And the 0.9344.
That was the 1.28 times 0.73.
And then 98.6 is from the other one.
Yep. And then I added the 98.6 to get rid of that on that side. So if you remember back to those horrible COVID years, when they had to scan you going in the door with those horrible temperature things that couldn't read a light bulb, like I had them put it on my head and go, it was 97.3. And I'm like, I'd be dead. Like something's wrong with your thing. But they were using it as 100. If you hit 100 degrees, that was their threshold for it. And if you look at this, 99.53 is in the 90th percentile. So you're getting up there. So if you were over 100, it's starting to become more and more of an outlier. Okay. So that's where those numbers come from. That's why they say when you get 100, you probably have a fever because it's not normal at that point. So, but it's not true about everybody. Not everybody has a mean body temperature of 98.6. It does vary a little bit. It varies by 0.73 degrees actually. So, all right. Let's do another one of these. Ooh, I like this one. Remember what I said at the beginning of class? If a teacher or one of those classes, I said if a teacher ever tells you the grading on a bell curve, run. This is why. All right. Figure out question A. Yep. And the nice thing is that's not going to change. Right. And if we do exactly what we did in the last problem, so 1.28, this time the standard deviation is 8, so times 8 plus 82 gives you a 92.24.
90% of that or lower. % or higher than that.
Yes. So remember, you're doing the same thing we just did here, except it's going to be 82 and 8. So you're multiplying by the 8, and then you're adding over the 82. So that means that the top 10% of the scores is above a 92.24, and 90% of the students would score lower than that. Yes.
Do you always use 1.2?
No, this one, because it was 90% again.
Oh, this is the-
Yeah, that's why we were able to use the 1.28 again, because it was the exact same, it was the 90th percentile, 90% same thing.
got it.
But yeah, if it was different, like we're gonna have to do a different one for the net and C when we do 80% of the scores. So, and this is why I said, if somebody tells you they're gonna grade on a curve, run. Teacher plans to give all students who score in the top 10% of scores an A. Will a student score 90 on the exam receive an A? No. Now, here's the interesting thing. What is the official score of an A at Three Rivers? $92.5. Or 93, like depending on how you round it up. 93 to 100 is an A. 90, 91, or 92 is an A minus. So, in actuality, that's about right. But if we're just doing the A, B, C, D, or A, B, C, D, F thing, some students would get a 90 or above and not get an A on the exam. Okay.
Then for 80, 85.
So now it says find the score that separates the lowest 20% of scores from the highest 80% of scores. So which percent of, so in this percent, we wanted to separate the top 10 from 90, right? So remember, for this one, we were looking at this part of the bell curve, correct? That's the 90%. What are we looking at in this one? We're looking at this, which is the 20%.
So I think 0.84.
So we're looking for 0.2. So 0.2. So it said we're separating the lowest 20 from the highest 80. So remember, whenever we're looking at the table, we're always going from the left over, right? So we're looking at this case, the lowest 20%, where in the previous problem, we were looking at the lowest 90%. That's why we use 0.9. This one we're using 0.2. So 0.2 on the table gives me negative 8 or 0.84. So my Z is negative 0.84. So now we're going to do the exact same thing I just did a minute ago. So 1.28, or not 1.28, sorry. Negative 0.84 times 8 plus 82.
88.72.
No. 75.28 is the score. Make sure you did negative 0.84.
Yeah.
So remember, z-scores can be positive or negative. If you're on the left side, it's negative. If you're on the right side, it's positive. That makes a difference. So my z in this case is negative 0.84. Right. We're below the 50%, so we're going to be in that negative area. So 75.28 is in the lowest 20%. Teacher plans to give all students who score in the lowest 10% of the scores an F. So will students who score at 65 in the exam receive an F? So now what are we looking for? We're looking for 10%.
That could be higher.
So I got 1.28. I got 1.28. So anyone who scores lower than a 72 basically gets an F. That's true scoring on a bell curve. Bottom 10% gets an F, top 10% gets an A. Then depending on how they split it up in the middle, 20, 25% gets the other. Majority of students will get a C. So in this case, an 82 would be a C. Most people wouldn't be very happy with that.
82, yeah, that's off the C.
Right. And that's the thing. So it's like when you're looking at grading on an actual bell curve, you're standardizing your test. So you're basically looking at it in terms of, okay, if my test was really easy, then this balances that scale out a little bit. If you're, but the opposite direction could also be true. If my mean was a 45 instead of an 82, a 45 would be a C, and you'd be happy. So it's depends on how that person does their things. I used to take my grades at the end of the school year every year, put all of my classes in one grade. Not when I was teaching high school, so I had like 200 kids. I'd throw them all in there and see where my mean was and where my standard deviation was, how my spread was. When I first started teaching, it was around like 70, 71, 72, right around there. I adjusted because I was a little hard. But some years it was up closer to 80 was the mean. It's like, okay, I was a little too easy. So it's like my goal was to shoot for my mean to be right around 75. That's the goal. The majority of the students should be in that middle range. You shouldn't have a ton of A's. You shouldn't have a ton of F's. So one of the reasons I got out of teaching high school is because that curve moved way to the right, where the majority of students now were in B's and A's. It's like, that shouldn't be either. So, but that's a true bell curve. That would be a true bell curve scoring. I don't know many teachers that would grade that way, except for some statistics teachers who are crazy. Most teachers couldn't figure it out. So, all right. Last thing we're going to talk about. So, what the last part we talked about on Wednesday last week was the binomial distribution. And we used a calculator to figure out like how, remember, binomial was two options, right? It was a yes or a no or heads or tails. It always had to be two options. Most of the problems that you had to figure out were very small, like 15 people, 10 people, things like that. What if I wanted to look at a sample of 2,000 people? And I wanted to know what the probability that fewer than 600 were going to work. That's going to be a lot of calculations and a lot of work. However, one of the things that happens is that a binomial distribution actually works out to be a nice bell curve. So if we were looking at a binomial distribution with n is 20 and p was 0.5, and it could be anything. It doesn't necessarily have to be 0.5. But in this case, it's 0.5. The curve, the probability when we plugged all those into the calculator that we were using would have come out to be exactly this, with a nice peak in the middle and a nice curve. Because it works out that way, we can use our stuff that we just did with the normal bell curve to calculate out our probabilities. So we don't have to go through and do all those massive calculations out. We can just do it with our z-scores. Just because we know the curve is going to work out this way. Okay. Okay, this is where I was. So the one piece that's important, though, is remember on these curves or in the uniform when we did, could we figure out the probability of one number? If I asked you for the z-score or if I said x was in the last problem that we did was 82, I want to know the percentage of people who got exactly an 82. Could you do it? No, because I need two numbers, right? Same concept with these. However, so when we're going to do it, if we wanted to find a single number, because single numbers can't exist in this situation, we have to do what I said at the beginning. We're going to do the subtract 0.5 and add 0.5. So for example, if we wanted to find 5, I would look at the x values for 4.5 and 5.5. And that's going to give me what's going to happen at 5. Okay? Does that make sense? So you're always going to subtract 5 and add 5. And those are going to be the values that you're going to use for your x terms if we're looking for a single value. All right. I'm going to do 5 in a second, but I want to do a little bit of this stuff first. I'm not.
And then you said subtract them?
Yeah, we'd get the values for each one and we subtract, just like we were doing before. When we found the two z-scores, we found the probabilities and we subtract them to find between them. We would do the same thing with this one. All right, so let's use these. To do all the stuff that we've been doing, what are the two pieces of information that I need to know before I can do anything? I need to know the mean and the standard deviation. Okay, so go back in your notes. What was the mean for a binomial distribution? No, that was temperature. This is from last class. Yeah. Nope, that was the beginning of this class. Last class. The mean was very simple. It's one of the last formulas we wrote down last class. NP. The mean is literally just n times p. No. That's the curve. Huh? Yeah.
Yeah,
Yes, expected value is the same formula for that one. Yes.
that's all.
That's what, okay, now I got what there. And then the standard deviation is the square root of n times p times 1 minus p. So we need those two pieces of information before I can do any of the work. So what's my mean for this one? Which is, right. Okay. And my standard deviation is 20 times 0.5 times 0.5. Because 1 minus 0.5 is still 0.5. So, and I got 2.24. The key is making sure you can get that number using whatever calculator you're going to use when you do your test. If you can't get that number, then you need to say something so I can make sure you can get that number. Everybody understand where the second 0.5 came from? That's 1 minus the 0.5, which is 0.5. These two numbers should always add up to 1.
Probably success is 0.5. So probably
Failure is also 0.5, yeah. All right. So we got the information we need. Now we can do question A. They want to know the probability that the random variable is 5 or less. So I'm going to use less than 5.5. Or equal to, because it doesn't really matter because there's not an equal to 5.5 anyway. Why am I using 5.5 and not 5? Right, because I want to include the 5. Remember, so these are all distinct values, right? This was when we were talking about discrete values. So these are all discrete values. There's no such thing as a 5.5 in this situation. No such thing as a 4.5. But if I want to include 5, I need to go above it. Otherwise, it's not going to include 5. It's going to look at everything below it. So I want to go to 5.5 to include everything there because we're basically taking that discrete concept and doing it on a continuous scale. I know it's confusing, but it makes our lives easier. Okay, so we're looking at when x is less than or equal to 5.5 and not just 5. Okay, does that make sense? Okay. So
Can you do P with that greater than so that it's 4.5?
no, because I'm not looking at exactly 5. I want everything less than 5. So I don't have to worry about the 4.5 in this situation yet. I'm just looking at 5 or less. So that's why I'm going to go up a little bit and go everything below that point. And the standard way, technically, you can use any number you wanted to go above it. We just typically use 0.5 in these situations. It's just the standard way to do it so everybody comes out with the same answer. So we're looking at 0.5. So now I got to find my what? I need my z, right? Because if I don't have my z, I can't find my probability. So my z is going to be the 5.5 minus 10, which is my mean, divided by 2.24. And I got negative 2.00 or 2.01.
And the 10 came down. Oh, okay.
So if I look at my negative 2.01, I get 0.0222222222. And if we use the calculator that we had before, that's what it came out with. So it's pretty close.
How did you get the 02069?
I used the calculator I told you to use last class.
It's calculator.net.
Yeah, it was Statology, those calculators, the probability distribution calculator on Statology.
We're doing this in Hawks. Do we need to use the methodology?
No. Do it. So it depends on which section you're using. Okay. If you were doing section 7.4, I think it was, or 7.5, the section we did last class, use the Statology one because this is the number they're expecting. If you're doing section 8, 6, I think this one is. Yeah, 8.6, you're using this calculator. Asking you two different things. And the question will say, so use a normal random variable, so it gives you that distinction in there. So the reason, like, you got to remember, a lot of the concepts and things that we do in math is because originally they didn't have calculators to do a lot of this stuff. Okay. So back 100 years ago, being able to do out the calculation like that would have taken a lot of work because they would have had to do each one individually to come up with those answers. And that's time and effort. So they figured out easier ways to do that, so they didn't have to necessarily use a lot more calculations to do it. By referencing everything to the normal bell curve, which they do a lot of other math with anyway, it saved them time. And they had the tables already created that they could easily go to the table and look to find those answers, so they didn't have to recalculate them constantly. And that helps. So that's the one thing we're looking at. Like now we have computers that can do a lot more of those higher end calculations quicker, but depending on how you do it, sometimes this is even faster to do. So, and it's always nice to be able to check what the computer is giving you to make sure that that's still accurate. And that's what I'm saying. Those two numbers are pretty close. Like that's within reasonable expectations. We're at like less than 1% or less than 0.1% off or something like that. So it's not that far off. So, all right. What if I wanted to find the probability that X is greater than 4? How do we do that one? I'm going to do greater than or equal to what? Why 4.5? Would it? If we're going greater than 4? Why 3.5? Because we want to go a little lower to go up, right? It all depends on direction. The last one, we were looking at less than 5, right? Or 5 and less. So if I go a little higher, I'm including the 5 as I go down. This one, I'm going the other direction. I'm going greater than 4. So if I start off at 4.5, the 4 is already forgotten. Go to 3.5, I'm going to hit the 4 as I go by. So we want to go greater than 3.5. So again, find my Z. So negative 2.90.
.9983. I mean. Oh.
This is 0. What number did you get before?
I was in the.
I know. What number did you get?
I got. I got .99813.
What do I have to do this number? Subtract 1 from it, right? What's 1 minus that? So, totally by shit luck, you figured out a way to use the table better. If we're going the opposite direction, if you look, now this is only going to work if you're literally going all the way to the end. Like if you're looking between two numbers, this is not going to work. But since we're going the opposite direction, if you look at the positive side of it, you will get the number.
That's what I checked.
You can use that to check, yep. And the opposite is also true. So like if we're looking at from 2 up and above on the standard deviation, if we look at the -2, get that answer, it's going to be the same thing because the bell curve is symmetric. Okay. So if I'm looking for, hold on, I just need a bell curve. If I'm looking for this section over here, or if I'm looking for this section over here, right? That right there is going to be the exact same as that right there. And the Z for this one will be the negative version of the positive Z there. So you can definitely do that. Okay. But it only works when you're looking at all the way over. If you're subtracting, it's going to confuse you and get you the wrong answer most times. Okay. But that can happen. So you had the right answer, just on the wrong side. Okay. I was waiting for somebody to come up with that answer, and it was like I was going to do that. Just took longer than I thought. All right. What if I wanted exactly 5? So now let's do the exact 5. So I want exactly 5. Can I do exactly 5? Right. So what do I have to do? I have to do both. This is where we go both directions. Okay, because if I want to look at just that one, I go both directions. So this one you need to find, well, we already have the 5.5, right? That's right there. So I don't necessarily have to do that one again. We do have to find the 4.5 one though. $2.46. And we already know the probability for, oh no, that's less than it. Yeah. So we already know that one's 0.0222. We just need to find the negative 2.46. Zero zero 70 0070. Oh, 69, you got it? Okay. So on the one that I'm using, it has the 5th decimal place, but if it's a 5, I can't know if it was that number was rounded up or. All right, and now we have to do what to those two numbers? Subtract. So this answer comes out to be 0.0153.
I mean, you can do it.
It doesn't make a difference.
One can be negative.
Right. If you did it the other direction, you're going to get a negative number. And you know you can't have a negative number. But if you just drop the negative sign, it's going to give you the same answer. What'd you get? I think you were off on your decimal point. No problem. I spent my 4 years in college working at a bank in the late 90s. And one of the things that, like, at that point, we had computers, but they didn't use them nearly as effectively as they were supposed to. So a lot of stuff was still done on a calculator, on a physical calculator with a tape going. And one of the things that I had to do was be able to take 2 tapes because everything was done twice. And if the answers didn't come out to be the same, find the error. Figure out which thing did they type in wrong. And some of these were long. So I got really good at being able to tell, like, if numbers were reversed, what number would show up at the end, if decimals were off, things like that. Really good at being able to tell those little mistakes. And I taught the people that were doing it so that they could catch their mistakes before they gave them to me. Yeah. And then I wrote a whole program that took over their bank. So I'm like, that's what I did. So Y2K, you know how everything is, oh, Y2K never happens. It didn't happen for a very important reason. We fixed the problem before it happened. It was definitely going to happen. Bad things were going to happen that day if we didn't solve the problem before that point. I had wrote a program that actually was going to basically take over the bank if their system failed. So I literally was on call that night. I could not go out and celebrate the Y2K, the big celebration and New Year's and everything else. I had to literally sit at home in front of a phone and wait for a phone call. I got paid very well to do that, so I'm not complaining. But I literally had to, because if something happened at midnight, my program was taking over and I had to go to the bank. So, and I literally wrote it all in Microsoft Access.
Yeah.
Huh?
I hate it.
It sucks now. There's lots better programs out there for it, but it was a very at that point, it was one of the better database systems to use. But yeah, that was what we did. All right. So we looked at an example. This is one thing. Let's see if so one of the things that we want to be able to start doing with statistics is being able to take a fact that somebody's stating and prove that it is either true or false. Okay. We want to be able to say, is what they're saying accurate or not? All right. And we can start actually doing that with what we just did. So let's look at this problem. Yes. Guess what? Real life examples are lots of words. But one of the things that you guys got to get better at is pulling out the things you need, because there's a lot of stuff in there that you don't need. Okay? So look at the numbers and look at where they fall into play with what we actually understand and know. What are the things that we actually need to know from we're talking, let's talk about. The agency claimed that 20% of alumni in the state were aware of the new campaign. Okay, so aware or not aware, right? So we're looking at what kind of distribution? Binomial, because it's only two options. Okay, so we can start to narrow down what we're looking at. Okay, if we're looking at a binomial distribution, we need two pieces of information, correct? We need N and we need P. Right? Those are the two things. If I get those two things, I can figure out a lot of stuff after that point. But I need N and I need P. All right, so let's look at this. So, all right, so it says the agency claimed that 20% of the alumni were aware of the new campaign. So P is going to be what? 0.2, 20%. To validate the claim, the agency developed a survey that 100 alumni in the state, so N, or 1,000. So we looked at 1,000 people, right? So that's N. And found that 150 were aware of the campaign. So that means my X is 150. Right? Okay. Let's do the calculations. So all those words, that's all we needed. So what's my mean? N times P. So 1,000 times 0.20 is 200. I'll find me my standard deviation. It's N times P times 1 minus P, right?
Yeah, 1,000.
Times 0.2 times 0.8. Which should give you 12.65. If you didn't get 12.65, my guess is parentheses. Because my guess is you did the square root of 1,000 times 0.2 times 0.8. Which would probably come out to be around 16. Or actually, you probably did the square root of 100, which you got 10. Yeah. Depending on your calculator, put parentheses around the 1,000 times 0.2 times 0.8, and you'll get the right answer. So 12.65.
Well, the square root of 60.
Yeah, it's the square root of 160.
Yeah, so 1,000 times 1.2 times 0.8 without parentheses.
Yeah. So 12.65. If you didn't get 12.65 and you'd like to figure out how you get to 12.65, just ask and I can show you on your calculator.
That's the standard deviation.
That is the standard deviation. No problem. All right, and we want no more than 150, right? Assuming the agency's claim is true, what is the probability that no more than 150 of the alumni in the random sample were aware of the new campaign? So that means we want less than or equal to 150, right?
No, less than.
Yeah, it's always it. Okay, so we're looking for, we're going to use not 150, we're going to use 150.5 for my X. All right, so Z, 150.5 minus 200 divided by 12.65.
-3.91.
Mm-hmm. All right, so are they telling the truth? That 20% of the alumni in the state were aware of the campaign?
Negative.
It's not because it's negative. If we looked up that number on the chart, if your chart could go that low, which the one in the book can't, yeah, it's 0.000005. Okay, so we're talking about basically nobody at that point. So we're not talking about basically nobody. We're talking about basically no chance that that's true. Okay, so if their claim of 20% was true, we would have expected more than 150 people to be aware of the campaign. Yeah. So in this case, their claim was false and they didn't do their job. Okay. And that's kind of where we want to look at these things. We want to start being able to make predictions and we want to be able to take a hypothesis and test it, see if it's actually accurate and true. Okay. So at this point, they failed, and I wouldn't necessarily pay them all the money that they expect because they didn't meet what they believe to be true. All right, so let's do one. Let me give you one more to do. All right, I'll give you one with a lot less words. There, a lot less words. And then there's the question.
High probability, right?
Huh?
Probably that will be very high.
That's what I want to know. I want to know what the probability is. Yes.
Deviation 7 point-
You use 39.5 and 80.5. Huh?
It's 7.6 deviation.
Hold on. Let me do it real quick. Hold on. I got it. 7.67. Yes. So your mean is $60. So then we're looking for 39.5 to 80.5. If we're looking at between 40 and 80. Mm, 2.67. And 2.67.
7.67, you did, the 3,000 times the 2% times what?
98%. Yeah, because that's the 1 minus point 1 minus 2% is 98%. So it should be 3,000 times 0.02 times 0.98. Remember, 2% is 0.02, not 0.2.
Yeah. I just wasn't sure about the 98.
Yeah, it's always 1 minus it. Remember, those two numbers should always add to 1. So 0.02 plus 0.98 is 1. So in this case, if you randomly picked 3,000 people, you'd expect if there was between 40 and 80 people infected, it would be 99% of the time you'd have that case. So you'd be pretty much assured that between 40 and 80 people are going to be infected in a sample of 3,000 people. We're looking at right now a binomial situation, right? It's a one or another. What we're going to start going into is being able to look at this in terms of situations that are not necessarily a binomial type situation. And we're going to be able to make those hypothesis tests about it. So, for example, you ever heard about cancer clusters? Where like there's certain areas that have a higher rate of cancer than other areas. They do that based on this kind of concept. They know what the general sense of cancer would be in the entire country in that type of cancer. And then they look at specific areas, and if their cancer rate is significantly higher than that, which means 2 or 3 standard deviations, depending on how accurate you want to look at it as, above, then that would be abnormal, and then there's something in the environment causing that. Okay, and that's how like we have a lot of those brownfield, that's right, sites. Like North State Hospital was one of them. It was like a very contaminated area, and it caused a lot of disease and cancers and stuff that came out of that because of that. And they can determine those based on these things. So that's what we're going to start going into is how can we start to use these normal distributions to start making those decisions and making those calls. Okay. All right. Your test is going to be on Wednesday. It'll open on Wednesday. It's on chapter 6 through 8. We are going to do chapter 9 on Wednesday. Okay. So you will have till Friday to complete the test. If I'm really, 11:59 p.m. If I'm really ambitious, the test will be there tomorrow. It just depends on if I get to it before between when I'm doing something else and going to the concert tomorrow night. So it depends on how ambitious I am tomorrow morning. Yeah, I should have the test. That's my plan. So it just depends on how much else I can get done tomorrow. But yeah, my plan is to have your test graded, so you'll have those grades on the test. You're welcome. You too.
Thank you.
Welcome. Yeah, I got the text. I'll, when I get home tonight, I'll send you the response because I know I have the way to do it. I just have to write it up. Have a good night. I'll text you afterwards.